So welcome to the next lesson or topic in biochemistry, vitamins. So by the end of the lesson you should be able to know what vitamins are, how the solubility can be predicted by its structure, that most vitamins are sensitive to heat, and have an understanding of vitamin deficiencies. You should be able to then compare the structures of vitamin A, C, and D, and discuss the causes and effects of vitamin deficiencies. Vitamins. So vitamins come under the kind of subcategory of nutrients. Okay, so nutrients can be broken up into macronutrients, which are substances that make up more than 0.005% of our body weight. They include the things we've been discussing previously: proteins, fats, carbs, and minerals. But basically, vitamins fall under the concept of micronutrients. They are organic micronutrients that cannot be synthesized by the organism in sufficient amounts, but therefore be obtained from either food or as food supplements. A lack of vitamins leads to cellular health conditions, which we'll outline during the lesson, and then sometimes can be fatal. And we also have cofactors, which are related to the enzymes, which we'll look more at in 8. So vitamins. They can be broken down into two forms. Okay, they are usually broken down in terms of their biological functions rather than their chemical structures. Many vitamins bind to enzymes as prosthetic groups or cofactors, while others act as hormones or antioxidants or to facilitate transfer of electrons. So in some cases, a series of structurally similar compounds showing the same type of activity have the same collective name. For example, vitamin A is actually a group of compounds rather than one compound in itself. Okay, so for example, vitamin B is a whole range of different open chain and heterocyclic molecules, whereas vitamin C refers to one particular compound, ascorbic acid. And vitamin D is actually, again, a range of different compounds. But by and large, they can be broken down into two classes: water-soluble and fat-soluble. So let's first look at vitamin A, the retinoids and carotenoids. So as we've already discussed in the previous slide, they are actually several organic compounds, the retinoids and carotenoids, and they perform similar chemical or biological functions. So retinol is a long chain alcohol with an extensive system of alternative single and double bonds, as you can see from a diagram. Because of all the carbon atoms involved in such systems, they have sp2 hybridization. The pi electron clouds of adjacent double bonds partly overlap with one another to form large clouds of delocalized electrons. Because of this is known as electron conjugation. It's similar to electron delocalization in benzene rings, which we've looked at previously, and produces a chain of carbon-carbon bonds with a bond order of about 1.5. In retinol, the electron conjugation involves 10 carbon atoms, including 2 carbon atoms in the 6-membered ring. Okay, there and there. So the carotenes, another group of vitamin A compounds, have even longer conjugation systems, which can involve up to 22 carbons. And they act as basically free radical mopper-uppers. Okay, they react with molecular oxygen and free radicals, and therefore all compounds are quite useful in antioxidants, and they also absorb visible light and therefore have bright, vibrant colors. Hey, that's why carrots are orange. Okay, they don't tend to have many polar functional groups, tend to be non-polar functional groups, which makes them essentially insoluble in water. However, like all hydrophobic compounds, group A vitamins are fat soluble, so they are absorbed through the intestine through certain lipids carrying them along and lipid proteins. As a result, low-fat diets tend to lead to problems associated with being able to absorb vitamin A, so you end up with vitamin A deficiencies. Okay, then we have the vitamin D. Okay, the collective name vitamin D refers to the cholesterol compound, which we see before us on the slide, and 3 other structurally similar organic compounds, which essentially, as you can see, that bond's been broken, but it looks kind of like a steroid. The human body, small amounts of cholesterol can be synthesized from its precursor 7-dehydrocholesterol. So this is actually coming from cholesterol in a way. The biosynthesis of this particular compound takes place in the skin and requires UV light. This allows the opening up of this ring, which you see here. However, when exposure to sunlight is limited, say if you're an Eskimo stuck in the high altitudes or latitudes during winter, vitamin D becomes an essential micronutrient that must be obtained not from the sun, but from the diet. The cholesterol molecules, large hydrocarbon backbone with only a single hydroxy group, makes it hydrophobic and highly insoluble in water. Therefore, it and other group D vitamins are fat soluble and can therefore be transported by biological fluids. They require lipoprotein complexes. In contrast to vitamin C, which we've just seen, natural sources and food supplements of vitamin D are usually rich in lipids and do not require additional fat intake for the vitamin to be absorbed into the body. So examples would be fish oil and liver, surprisingly eggs and mushrooms. So the 2 former are quite good if you're an Eskimo because you eat a lot of fish. Then we have the vitamin C. Okay, so vitamin C is essentially just one compound. It's known as ascorbic acid, okay, which we see here in great resolution. And it has basically multiple polar functional groups, which are very oxygen rich. And these several hydroxyl groups and ester fragment in the molecule can form multiple hydrogen bonds with water, making it a very water-soluble vitamin. Same polar functional groups make ascorbic acid insoluble in fat, so it cannot be stored in the body for a long time. So that means you have to take it in regularly, which isn't so great if you're a sailor. Hence, in the human body, vitamin C participates in a broad range of metabolic processes, including the biosynthesis of collagen. Okay, and this is the reason why when you have scurvy, your connective tissues essentially break down and your skin basically falls from your body. You get loss of teeth, gum problems. Ascorbic acid is a powerful antioxidant and reducing agent capable of donating 1 or 2 electrons to biochemical redox reactions, which is also quite useful. And basically, the concentration of vitamin C in solution can be determined by a redox titration, which we've looked at previously, which is a great IA if you'd had the chance, using DC-PIP or 2,6-dichlorophenylindophenol as an indicator. And in the presence of ascorbic acid, the pink color of the protonated indicator becomes colorless as it is reduced. Along with other antioxidants, ascorbic acid is commonly used as food additive E300 if you're looking on your packets, and it prevents the oxidative rancidity we looked at when we're looking at lipids. So there's a whole range of nutritional diseases. Okay, here's another group of examples. So if you're deficient in iron, then you get something called anemia, and you're basically very tired, very common with women, okay, because you don't tend to have a very high iron diet. Iodine, you get goiter, which isn't quite common anymore because they tend to put iodine in people's salt, but it is seen a lot in, say, sub-Saharan Africa. And iodine also can cause a level of mental retardation if it's not ingested. Niacin, vitamin B3, forms pellagra, which can lead to problems with the skin, dermatitis, and dementia, because you can't essentially process iron. Vitamin B1 causes a disease called beriberi, which causes weight loss, fatigue, and swelling, quite common in the tropics where we are at the moment. and lack of protein, which again is quite common in sub-Saharan Africa due to the lack of diet, causes marasmus, which is a weight loss in infants after weaning from mother's milk, which of course is high in protein, and kwashiorkor, which is a weight loss in infants with high starch, low protein diets, again found quite commonly in sub-Saharan Africa. So in terms of health, malnutrition, as you can see from those images, is a lack of regular balanced supply of nutrients. We don't tend to have that, the opposite in the West is maybe obesity and diabetes due to too much nutrients. But those micronutrients are not in high supply in our Western diet. So ways to improve world health could be providing food rations which are composed of fresh and vitamin and mineral-rich foods, fortification, including adding nutrients missing in common consumed foods. So that was the iodine to salt example, adding vitamin A, B, D to rice, for example, which they're doing in India through GMOs. Genomic modification of food, as I just said. Oh, gee, should really read on. Providing nutritional supplements and providing, say, selenium supplements for people eating foods grown in selenium-poor soil, which is quite common actually in New Zealand. So that's pretty much all you need to know about deficiency diseases. Not the most inspiring topic with the deficiencies, but it's something you can hopefully look to improve world health with by knowing the causes and alleviating those, in especially the third world.